Hi students, in this video I am going to discuss about the differential length, area and volume concepts using the analytical approach. I have already discussed the differential length, area and the volume concept individually when I discussed each and every coordinate system. That means for Cartesian, cylindrical and spherical coordinate, I have written some formulas for differential length, area and the volume. At that portion, I also told you that after completion of the all coordinate system, I will discuss a short trick or a Brahmastra trick, you can say, by which you can easily remember all the formulas of differential length, area, and volume in case of any coordinate system. Okay, so let me show you the trick first. But before that, I want to show you one table. Okay, let me draw this table first, because this table is actually the trick. Okay. The main trick is nothing but this table. Okay. In this column, in the first column, I will write the name of the coordinate system. So that's why I am writing here the nothing but the coordinate system. Okay. Then after that, I will write the unit vector, that is AU, AV, AW. These are the unit vector in the direction of UV and W, and where UV and W are the parameters. Okay, I am trying to write the generalized form over here. After that, I will try to write the individual forms in case of each and every coordinate system. And the difference for the differential length, the du, dv and dw will be written over here in this column, and another term that will come into this picture, that is h1, h2 and h3. Now h1, h2, h3 are the parameters. Okay, right. Now I will denote these things over here also, don't worry. U, V and W are the parameters. U, V and W are the parameters. And one more thing, that is H1, H2 and H3 are the scaling factors. They are called the scaling factors. They will be used in differential length, area and the volume formula. Okay. These two things you have to remember. Now, let us talk about the different coordinate system. First, let me write the Cartesian coordinate system. Okay, just a minute. Let me write it clearly. Okay. This is the Cartesian coordinate system. In case of the Cartesian coordinate system, the unit vectors will be ax, ay, and az. And du, dv, dw will be dx, dy, and dz. And h1, h2, h3 is nothing but the 1, 1, and 1. You have to remember this scaling factor in case of each and every coordinate system. Okay. Now, come back to the next coordinate system, that is the cylindrical coordinate system. That is called the rho phi z coordinate system. A rho, a phi, a z coordinate system. That is the d rho, d phi, dz, definitely, because the cylindrical coordinate system is also known as the rho phi z coordinate system, and the scaling factor will be 1 rho 1. Okay. The third type of coordinate system is spherical coordinate system. That is also called the r theta phi coordinate system. That's why the unit vectors are ar, a theta, and a phi. See, I have shown the unit vectors in the main diagram of the spherical coordinate system, Cartesian coordinate system, and cylindrical coordinate system. I think you have remembered it, in which direction they are actually directed in the diagram. Okay. So du, dv, dw for spherical coordinate system will be what? Dr, d theta, and d phi, because it is the coordinate system of the r theta phi, and scaling factor will be 1 r, r sin theta. Okay. This table is very, very important to write the differential length, area, and the volume. Okay. So remember this table, very, very important it is. I am putting here 5 star. It's not about the 5 star chocolate. It is the 5 star means very important. What is okay? Now I will write the differential length formula. Now that is nothing but the generalized formula. Just a minute. Okay. My machine is hang on. So just a minute. That is the generalized formula. For differential length. That is what? What is the generalized formula for differential length? Using all these three parameters, UVW. Okay, I will not write it like this because it will be very much confusing. So I'm writing directly dl equal to, because it will be very much confusing otherwise. So our first is dl. dl equal to what? See the generalized formula for the differential length. What is the generalized formula for differential length? That is, I'm writing it over here. H1 du au. Okay. That is H1 du in the direction of au plus H2 dv in the direction of av plus H3 dw in the direction of aw. Okay. This is the actual equation in the case of the differential length. Very important. And actually, it is the generalized equation. Okay. In case of the differential length. Now let me write this differential length for Cartesian coordinate system. I think it will be easy for you. But I am writing the differential length for the Cartesian coordinate system. DL will be what? For Cartesian coordinate system, H1 du au means basically I am pairing it like this. With du, I am pairing the H1. With dv, I am pairing the H2. And another color, let me take another color. That is what? That is nothing but okay. With dw, I am pairing the H3. So that's what I have written over here also. H1 with du, H2 in dv, and H3 with dw. Okay. So dl will be equal to, dl means I am talking about the Cartesian coordinate system. Let me mark over here also. Otherwise, it will be very much confusing for you. H1 du au, that is nothing but 1 into dx into x plus H2 dv av, that is 1 into dy into ay. I am writing it directly like dy ay plus H3 dw aw, that is 1 into dz into az. That is, I am writing dz az. Very much easy. This is nothing but for Cartesian coordinate system. Similarly, for cylindrical coordinate system, what will be the differential length? For cylindrical coordinate system, the same formula, the same generalized formula I will follow up here. H1 du into AU. That means 1 into d rho into a rho. 1 into d rho into a rho plus H2 dv AV. That is rho into d phi into a phi. Rho into d phi into a phi plus H3 dw is AW. That is 1 into dz into az. That is 1 into dz into az. Okay. That will be what? Let me write it like this. It is d rho a rho. Just a minute. Plus rho d phi a phi plus dz az. That is for cylindrical coordinate system. In the same way, I can write it like the spherical coordinate system. The same formula I will follow up here. It is 1 into dr into ar, dr into ar plus r into d theta into a theta, r into d theta into a theta plus r sin theta into d phi into a phi, r sin theta into d phi into a phi. Okay, and in the organized way, I will organize it like this: dr ar, r d theta, a theta, and r sin theta d phi a phi. For spherical coordinate system. Okay, now this was the generalized formula for differential length. Now I will show you the generalized formula for differential area. Okay. Now the differential area is a vector quantity. It must have the three directions. Okay. So as it has the three directions, it also have the three different formulas. The first formula is ds in the direction of AU. Dx in the direction of AU, that is nothing but, see this point very carefully. In case of the differential area, what I told you, that is nothing but among u, v, w, among u, v and w, if any two parameter gives you the volume, gives you the magnitude of the area, then the remaining parameter will give you the direction of the area. Okay, that I have told you in earlier way. In my earlier coordinate system, when I have taught each and every coordinate system, in almost in each coordinate system, I have told you like if among the three parameters, if any two parameter give you the magnitude of the area, then the remaining one parameter will give you the direction of the area. Okay. What is the area ds? Now, first of all, I am trying to write the area in the direction of AU. If I try to write the area in the direction of AU, so along in the direction of EU, it is giving the U is used here to give the direction of this area. Then the remaining parameter V and W will be used to determine the magnitude of this area. Okay, so that will be what? See this V and W. That means nothing but H2 into dV and H3 into dW. These two will be used to determine the magnitude of the area. That means I will write to it over here H2 into dV into H3 into dW. Okay. Okay. As you have seen over here also, that is H2, H3 and H1, these are the three scaling factor. So it will be always multiplied with du, dv, dw. Okay, the scaling factor will always remain in any formula that may be of differential length, that may be of differential area, that may be of differential volume. So in each of these formulas, the scaling factor will be present, right? So in the similar way, the differential area, another differential area that will be in the direction of AV. That will be what? As the V is used, the parameter V is used to determine the direction, then the U and W parameter will be used to determine the magnitude. So that means nothing but the H1 into du and H3 into dw. Okay, this is one important formula of the differential area used in the direction of AV. Okay, and ds in the direction of AW. Now the parameter W is used to give the direction. So that means parameter U and P will be used to give the magnitude over here. That is H1 du into H2 dV. That means nothing but the U and V has been used over here to determine the magnitude. And in the similar way, the W parameter has been used here to determine the direction of the area vector. Now, depending upon this, I can write the differential area in U, V and W direction, okay, for each and every coordinate system. Like in case of the Cartesian coordinate system, I can write the differential area as what? Just by looking at these, okay, just 1 minute. These are the normalized formula. So very important. I am putting 3 star over here. Okay, so mm, now let me write the differential areas in all these three directions. Okay, in all these three directions, based upon this normalized formula. Our first formula is what? Now see, in case of the Cartesian coordinate system, I am trying to write. Okay, that is H2 dV into H3 dW. Okay, what is the H2? H2 is nothing but the 1 into dV. In the dV, the Cartesian coordinate system is nothing but the dy. So dy, and that is nothing but the H3 into dW. H3 is 1 over here, and dW is what? Dz, and in the direction of AU. has been denoted in case of the Cartesian coordinate system x. Okay. Now h1 du and h3 dw. Okay. In case of the Cartesian coordinate system, h1, h2, h3, all of three are 1. So 1 into du means dx into 1 into dw means dy. I'm sorry, dz in the direction of ay. And similarly, what will be the ds? h1 into du, that is nothing but 1 into dx into 1 into dy in the direction of az. Okay. I have written here it in case of the Cartesian coordinate system, right? Now, in case of the cylindrical coordinate system, let me write these things. ds. Cylindrical coordinate system h2 and h3 is what? Rho and 1. So, rho, dv and dw are nothing but the d phi and dz in the direction of au, that is arrow. In a similar way, I can write the differential area in the direction of av means phi. In the direction of phi, I can write the differential area for in case of the cylindrical coordinate system, that is nothing but what? h1 du and h3 dw. h1 and h3 is nothing but 1 1. So u du and dw, these two things will be d rho dz. Okay. In the similar way, I can write the differential area in case of the spherical coordinate system h1 into, I'm sorry, for cylindrical coordinate system in the direction of z. In the direction of z, h1 and h2 will be nothing but 1 and rho. So I'm trying to write rho over here first. Then du is nothing but the rho d rho dv. That is nothing but the d phi. Rho d rho d phi. Okay. And the third one coordinate system is nothing but the spherical coordinate system. That is h2 and h3 are nothing but r and r sine theta, right? In the table, according to the table, see, you can see over here, that is h2 and h3 are nothing but the r and r sine theta. Okay. And that is in the direction of what? In the direction of AW. I'm sorry. First of all, I'm trying to write the differential area in the direction of the AU. So that means nothing but in the direction of AR. So I can write R into R sine theta. That means R square sine theta d theta d phi into AR according to this formula. So that is nothing but the R square sine theta d theta d phi in the direction of AR. Similarly, I can write the ds because of the spherical coordinate system in the direction of what? In the direction of theta. h2 into h3, that is nothing but the 1 into r sine theta. So r sine theta du dw, that is nothing but the dr d phi. Now, in the direction of phi, that is nothing but H1 H2, that is nothing but the R, and du dv nothing but the dr d theta. Okay. H1 and H2 are what? 1 into R. So that means I have written R over here. So R dr d theta in the direction of phi. This was about the differential area. Okay. Now I will write the generalized formula in case of the differential volume, which is very easy. H1 into du dot H2 into dv dot H3 into dw. No directional vector over here. As you know, the differential volume is what? That is nothing but a vector scalar quantity, right? Differential volume is nothing but the scalar quantity. Okay. And one more thing, this is the generalized formula. So let me put it like this. Okay. So what is the differential volume in case of the Cartesian coordinate system? H1, H2, H3 are, in case of the Cartesian coordinate system, they are 1, 1, 1 according to the table. So I am just not considering that 1 into 1 into 1 because it will be nothing but the 1. Now, du, dv, dw, that will be nothing but the dx, dy, dz. Okay. Now, the dv in case of the cylindrical coordinate system, this was all about the Cartesian coordinate system. Okay. Now, cylindrical coordinate system, h1, h2, h3, 1 row 1, 0, d phi, dz. Rho d rho d phi dz, because 1 into rho into 1, that is the rho, du is nothing but the d rho, dv is nothing but the d phi, and dw is nothing but the dz over here, because I am talking about the cylindrical coordinate system, and you know that is the, in case of the cylindrical coordinate system, we can also write the parameters u v w as rho, phi, and z respectively. Okay. Now the last coordinate system, that is nothing but the spherical coordinate system. Because of the spherical coordinate system, the dv will be h1 h2 into h3, that will be 1 into r sine theta, that is nothing but the r square sine theta, and du into dv into dw, that is nothing but the dr d theta and d phi. Okay. And that is nothing but the spherical coordinate system. In case of the spherical coordinate system, I have written it like this. Just by maintaining the normalized formula, you can write differential length, area, volume in case of the any coordinate system. And just by remembering this table, you have to remember this table only, and you have to remember just this differential length, area, and the volume formula. And this formula is very much easy, right? For differential length, you can see this H1. As you can see, that is H1 is always associated with the du, H2 is always associated with the dv, and the H3 is always associated with dw. In case of the any formula, the same thing I am going to use here. In case of the differential length, you know the formula of the differential length, as differential length is a vector quantity. It must have the three directions, and it must have the three component in the three directions. What are those three directions? Those are nothing but the AU, AV, and AW. And as those three directions are the AU, AV, and AW, so differential length component will be this H1 into a du plus H1 into du into AU plus H2 into dv into AV plus H3 into dw into AW. And a similar way it will occur. This is the formula of the differential length. Similarly, for differential area, in case of the differential area, you have to remember a single thing. What is that? That is nothing but the, if you take u parameter to, if you use the u parameters to determine the direction, then the remaining two parameters like v and w parameter will be used to determine the magnitude. Now, in case of the magnitude, you have to just multiply this to h2 into dv into h3 into dw. Okay, always multiply the scaling factor with dv, dw, and du. Okay, don't forget to multiply the scaling factor. In the similar way, in the direction of AB and AW, I have written the differential area formula over here. And the differential volume formula is very much simple. That is what? That is nothing but a scalar quantity. As this is a scalar quantity, it doesn't have any directions, means doesn't have any unit vector in any directions. So that means the differential volume will be multiplication of all these three, U, V, and W. That means H1 into du into H3, H2 into dV into H3 into dW. Okay. So that is like this. Okay. And depending upon this normalized formula, I have discussed about the I have discussed about all of the differential length, area, and the volume concept in case of the any coordinate system. This is called actually the analytical approach. Actually, the previous one approach, whatever we have discussed by using the graph or the coordinate system, those are called the graphical approach. And this is called the analytical approach. Okay, so that's all about it. About our coordinate system. I have completed all things that is possible that may come into your exam in case of the coordinate system. In my next class, in the first chapter, there is another topic is remain, that is nothing but the vector calculus. In my next class, I will dive into that vector calculus part. Okay. So that's all for today. Keep watching my videos and thank you.